Let's take a look at standing waves. So, way back when we introduced waves, I said that a wave is something that transfers energy in the direction of wave motion or wave propagation. Well, what if we have a situation where the wave is reflected back and then interferes with itself? What would happen there? Well, let's draw a picture first before we think about it. Here's the incoming wave, and here's kind of a fixed point, a fixed boundary. And the wave is going to reflect back, and we'll get something like this. And if that looks a little complicated, it kind of is. Now, what if we made it even worse? What if we have the wave, but it's stuck between two points, two fixed points? So it just keeps reflecting off of one end and then off the other, and it just keeps going back and forth. Well, that situation is called a standing wave. It's a situation where a wave is confined in a space or a volume, and it reflects back upon itself. Now, this can be a little bit tough to visualize. I'm going to try to put a link to some visualizations in the YouTube comments. But here's the result. We get something that might look something like this. Now, this is just one example. We'll see many examples in a moment. But here's a fixed point. Here's a fixed point. We're going to imagine a string between it. And we'd get a string that would vibrate like this. So it's vibrating between these two lines. It's oscillating between those two lines. And you can see there are places on the string that do not oscillate. These are called nodes. There are also places where the amplitude of the oscillation is large. Where it's largest, that's called an antinode. Also notice there are places where the wave is oscillating in phase, and there are places where it's oscillating out of phase. And in fact, the adjacent antinodes are out of phase, and to find an antinode that's in phase, you have to skip over one. So throughout this standing wave, the medium is oscillating everywhere except at a node, and the amplitude of the oscillation in the medium varies with location. All right. So I'm going to draw a lot of diagrams soon. So I just want to say at the outset, standing waves are a very visual idea, and it's going to require a lot of diagrams. So just be aware of that and try to draw them as accurately as possible. And we're going to look at three different cases of standing waves. We're going to look at the case of two fixed ends, a case of two free ends, and a case of a fixed end and a free end. So when we consider standing waves that have fixed ends, this is situations where the medium is required to be stationary on the two ends of the standing wave. So this could be a situation like the string on a guitar, or the string on a violin, or the string on a harp. In all of these situations, at the two ends of the string, two ends of the medium cannot oscillate. It's stuck, it's fixed at a node. So let's imagine that. I'm going to try to draw the largest possible wavelength I could get in this situation. It would look like that. The wavelength in this situation is equal to twice the distance between the ends. And we're going to call the distance between the ends L. So here, a wavelength is equal to 2L. I can also write an expression for the frequency. Here the frequency is C over 2L. All right. Now, the next possible wavelength would look like this. Okay. Now, here, a wavelength is just equal to L, and the frequency is equal to C over L. All right. And then the next largest would look like this. And this is a little different. But if we imagine splitting the wave or splitting the length into thirds, one wavelength is 2/3 of that full length L. So a wavelength is equal to 2/3 L. The frequency then is equal to 3C over 2L. And then the next largest would look like this. And in this situation, a full wavelength is half of L. And the frequency is equal to 2C over L. Now, we name these. The first one, that biggest one up there, is called the fundamental frequency. We also call it the first harmonic. And each of the other waves are named based on this harmonic. The nth harmonic, we say, has a frequency equal to n times the fundamental frequency. So this one right here is the second harmonic. If you look, the frequency is twice that of the fundamental. This is the third harmonic. the frequency is equal to 3 times the fundamental. This is the fourth harmonic. Frequency is equal to 4 times the fundamental, and so on. All right. Now let's look at a situation where we have two free ends. This would be a situation like panpipes, where the requirement is that at the two ends of the medium, we have antinodes. So here's the largest wavelength we could get. Here's the next largest. All right. Here's the next largest. Okay. And then the next largest. And if I write down the wavelengths for these, what you'll notice is that the wavelengths for the free ends, the two free ends, the wavelengths are exactly the same as for the two fixed ends. And the frequencies are the same too. And we name the harmonics the same way. All right. Now, the one that we haven't looked at is the one that has one fixed end and one free end. So this would be a situation like most organ pipes, or if you're blowing into an empty bottle, say. So in this situation, here is a fixed end, here is a free end. The largest possible wavelength we could get would look like this. There's one fixed end, one free end, one node, and one antinode at the free end. So in this situation, the wavelength is 4 times L. In order to get a full wavelength, it would have to be 4 times the length of the pipe. And the frequency would equal to C over 4L. Now the next largest would look like this. All right. Now this is a little bit weird, but if we split this into thirds, that's 3/4 of a wavelength. So a wavelength, then, is equal to 4/3 of the length of the pipe. Okay. So then we can also write down the frequency of that situation. Now the next largest would look like this. Now imagine splitting this length into 5 equal parts. One wavelength is 4 of those parts. So a wavelength is 4/5 of L. And then frequency is equal to this, 5C over 4L. And then we could do another one. Here's the next largest. And here we'd split it into 7 equal parts. And 4 of those parts would be a wavelength. So the wavelength is equal to 4/7 of L. And then the frequency is equal to 7C over 4L. We can name this. We can name this the fundamental frequency. And then this one right here, if you notice, its frequency is 3 times the fundamental frequency. So this is a third harmonic. And then this one right here, this is a frequency that's 5 times the fundamental. This one has a frequency that's 7 times the fundamental. So we have a fifth harmonic and a seventh harmonic. Notice that in a situation with a fixed end and a free end, we only get the odd harmonics. There are no even harmonics in a fixed free end situation.